All right, class. So I have here for us today the solutions to our calorimetry problems, those practice ones that I put up. So the first one, you have two containers. Each of them have water in them. In the first one, I have mass is 100 grams, mass is 100 grams. Then I have 5 degrees Celsius in one and 80 degrees Celsius in the other. Now they're both water, so they have the same specific heat. 4.18 is the magic number for the specific heat of water. Okay, so I've got all my, I've made a little picture, I've got all my data here, and what we want to do is we're going to pour these two quantities of water together, and we're going to see, we want to think about, okay, so what temperature is the mixture of this going to be in the end? So to use our equation, I have M1C1 times, and so this is mass 1 times specific heat 1 times the final temperature minus the initial temperature. And this is all of thing 1 equals negative the mass of thing 2, specific heat of thing 2, times the final temperature of thing 2 minus the initial temperature of thing 2. Okay, so a few things to note as we kind of look at this and move forward. Number one is these T finals will always be the same, okay? And that's because we're taking the two things and we're mixing them together. The whole point of this is to figure out what final temperature do we eventually arrive at, all right? And so, all right, so that's the point of all of this, right? So I know that the final temperatures are going to be the same in each case. So that's important. The other thing we want to look at is, okay, well, there's a minus sign over here, but there's not a minus sign on the other side of the equation. So which quantity is going to be negative? Okay, and to figure that one out, you just come back here and look at the original things and say, okay, well, which one's hot? Okay, well, so this water is the hot water, right? It's 80 degrees Celsius. That's kind of close to boiling. And this one is going to give its heat to the other one, right? So this one is going to be thing 2 for us. It's losing heat to the other thing, which is what makes it negative, okay? So when I plug my numbers in, you're going to have 100 times 4.18 times, I'm just going to write this as T. I know that they're both going to be the same, minus, this is the cold one, 5 equals negative 100 times C, which is 4.18, times T minus 80, and that's the hot one. Okay, great. So now I can kind of run through. Now, with this problem, I mean, I've picked some nice numbers here for myself and for you. The masses are the same, right? So those 100 will divide out. The specific heats are the same, so those will divide out, right? So I'm left with T minus 5 equals, take this negative, distribute it in, negative T plus 80. Okay, so I'm going to add T to this side, I'm going to add T to this side, and I'm going to add 5 here, and I'm going to add 5 over here. So I have 2T equals 85. Divide the 2, and the final temperature of my water mixture is 42.5 degrees Celsius. And this makes sense, right? 42.5 degrees Celsius is the number that's exactly in between 5 and 80. Now, the reason why that makes sense is because their specific heats are exactly the same and their masses are exactly the same. So with those two quantities being the same, I know that I'm going to meet, the temperatures are just going to meet in the middle, right? So that's kind of a nice, easy one to get started with. The next problem, on the other hand, isn't quite as simple. There's a little more going on in this problem. And so for this one, let's see here. I have thing 1 and thing 2, and in thing 1 I have water, and in thing 2 I have oil. So let's see, I have 50 grams of the water, 40 grams of the oil. The water starts out at 90 degrees Celsius, and the oil starts out at 15 degrees Celsius. The specific heat of the water is 4.18, and the specific heat of the oil is 1.97. Okay, so let's set up our equation, right? So I have M1C1 times T final minus T initial equals negative M2C2 times T final minus T initial. All right, let's put our numbers in. Okay, so which one is going to lose heat? And so if you look at this, right, the water is going to lose some of its heat to the oil because the oil's got to heat up and the water's going to cool down. So the water stuff's going to go on the loser side. I should say the losing side. Nobody's a loser in any case. Anyways, so my cold thing. So I'm gonna have 40 times 1.97 times T minus 15 equals negative 50 times 4.18 times T minus 90. All right, and I'm set up. And I can check, right? My negative side has the hot temperature, positive side has the cold temperature. Feel like I've got a T on both sides of the equation, so I can solve for it. To do that, I'm going to take this quantity and distribute it in. I'm going to take this quantity and distribute it in and over here. Okay, I like to write it all out like this. You may want to multiply things together and move around decimals, but I don't like to, I don't know, I just like to do it this way. So 40 times 1.97 times T minus 40 times 1.97 times 15 equals negative 50 times 4.18 times T plus, right, the negatives are going to make that positive, 50 times 4.18 times, I fit it in there, 90. I didn't think I was going to make it. All right, so where do we go from here? Well, I need to get my T's on the same side, and if you look, so this one's negative, so I'm going to add this number over here, and this one's negative, so I'm going to add this number over here, and when you do that, this becomes 40 times 1.97 T plus 50 times 4.18 T equals 50 times 4.18 times 90 plus 40 times 1.97 times 15. Okay, now at this point in the problem, you realize, hey, there's a T in each of these terms, so I can pull that T out in front. So it's not there anymore. I pulled it out. And so I'm going to take this thing, I'm going to divide by this number. I'm going to divide all of this by that number. And so T is going to equal, now when you do this, you got to be really careful. You've got this massive thing on the numerator. You know, if I was putting this in my calculator, I'd probably run all of this into my calculator first, hit equals, have a number, then hit the divide sign, and then whatever you put in the denominator there, you had better make sure it's surrounded by parentheses, or else your calculator is going to give you fits. But if you entered that into your calculator correctly, you should get the number, or at least I'm getting the number, 69.46 degrees Celsius. Okay, now that we have this answer, we want to look and ask ourselves, and this is the beautiful thing about science, is you can check your number and you can say, okay, does this even make sense? So if I come back up here and compare this to where we began, this is basically 70, right? That's approximately 70. So 70 is much closer to 90 than it is to the 15. And we want to ask ourselves, okay, does that make sense at all? And so let's look. I do have a little bit more mass of the water than I do of the oil. So with that higher mass, I would expect the temperature, that would give a point towards it being closer to the water than to the oil. The other thing is if you look at their specific heats, right? And this is, the specific heat, its unit is joule divided by gram degrees Celsius. So for example, for this oil, it takes 1.97 joules of energy to take 1 gram of oil and change it 1 degree Celsius. Okay, so in other words, if I'm looking at this, this is basically 4 and this is basically 2, right? This is twice as big. So it takes twice as much energy to change the temperature of water compared to the temperature of oil. Okay, so in that regard, this is going to be much closer, right? The temperature should be much closer to the water because its temperature is so much harder to move than the temperature of the oil. And that's exactly what we found here, right? This 70 shows me that yes, it is closer to the water, right? The oil went from 15 and it raised all the way up to 70. The water went from 90 and fell to the 70. So a much bigger change for the oil, but that's exactly what I would expect based on the specific heats. Okay, so there is that. Let's move on. All right, in the third problem, we've moved on to solids. So I've got a hunk of metal, and that's a hunk of metal, and I have a container of water. And my stats for these things is I have 1,000 grams of metal at 1,500 degrees Celsius. And this is iron. The specific heat of iron is 0.444. And I have 8,000 grams of water at 20 degrees Celsius, and the specific heat of water is 4.18. Okay, so I mean, you look at this. I looked up, by the way, so this is iron, and you know, I was thinking of forging, but anyways, so this 1,500 degrees Celsius is almost at the melting point of iron. So this iron is almost ready to melt, and I'm going to take it and I'm going to drop it into this water, right? It's at 1,500 degrees Celsius, and I want to know what's the final temperature of this thing going to be, right? Because blacksmiths, they heat their stuff up, they pound on it for a little bit, and then they chuck it in a bucket of water. I think it's salt water, or it's, I don't know, it's something, to quench it. And all right, and there's a temperature exchange there between the two things. So let's figure out what is the final temperature of this mixture going to be. Now notice the water's temperature is really hard to move, and I have 8 times as much water as I do iron. Okay, so you know, looking at this, the water, the quantity of water that I have, its temperature is going to be much more difficult to change than the little piece of iron I'm working with. Okay. All right. So setting up my equation, M1C1 T final minus T initial equals negative M2C2 T final minus T initial. Okay, so this is the hot thing. So this is going to go over here into the minus sign. It's losing heat. So so this is going to be 8,000 times 4.18 times T minus, oh, I erased my temperature there a little bit. This is 20. T minus 20 equals negative 1,000 times 0.444 times T minus 1,500. All right. So, I mean, this is essentially the same problem as before, just different numbers. One of the things I can do here is these are both in the thousands, so I can divide the thousand part of it out. So I just have less numbers to write. So when I distribute this thing in, I have 8 times 4.18 T minus 8 times 4.18 times 20 equals, distribute this in, so I'm going to have negative 0.444 T plus 0.444 times 1,500. Okay, so then just like I did before, I'm going to add this thing over here. Well, I'm going to add it to this, really. And then I'm going to add this quantity over here. And then that leaves me on this side with 8 times 4.18 T plus 0.444 T equals 0.444 times 1,500 plus 8 times 4.18 times 20. And then again, I'm going to distribute this T out. And then I'm going to divide this number right here. I'm going to divide that over here. Okay, and so when you do all of that, and again, being very careful with how you enter things into your calculator, I ended up with a final temperature of 39.39 degrees Celsius. So now, right, we want to look at this. So we're basically at 40, okay? So if you look at the temperature of your water doubled. You had 800 grams of water and you doubled its temperature. But the temperature of the iron here went way down. It went from 1500 degrees Celsius to 40 degrees Celsius. So does that make sense? And I look at this and I say, okay, look, water has a huge specific heat compared to the iron. It's much, much harder to change the temperature of water than it is to change the temperature of iron. And I also had 8 times as much water as I did iron. So I do feel okay saying that the temperature of the water only went up 20 degrees, whereas the temperature of the iron went way down. And by the way, this is why, right, you have this in blacksmith shops, you have giant quenching buckets that they put little pieces of metal into, because that water can accept all of that heat without changing its temperature very much. Now, one of the things that I am ignoring here is that if you take a piece of metal that's this hot and chuck it into the water, you're going to get a ton of steam coming out, and that steam also carries away with it copious amounts of energy. So much energy. It takes a lot of energy to change the phase of the water from liquid to gas, but that's a completely different lesson than this. So in our problem, we assume that none of the water boils off, that it all stays as liquid, and this would be the final temperature. In reality, the temperature would be lower than this because of heat lost as steam boiling off of it. Anyways, so last problem. And luckily, the math on this one's a little bit easier. So in this one, you're given some random hunk of something. Don't know what it is. And it has a mass of 75 grams. And it starts, well, you take it and you heat it up to 100 degrees Celsius. And you need to know what its specific heat is. And then over here, you've got a cup of water, and the mass of the water is 200 grams. And your starting temperature for the water is 10 degrees Celsius. And the specific heat of the water is 4.18. Okay, so here, right, you need to know what the specific heat of this object is. So we've heated it up to 100 degrees Celsius. We're going to put it into the water, and we're going to see, okay, well, what we know, we measured that the final temperature of the mixture when we were done was 85 degrees Celsius. So now you look at this and you say, okay, oh my goodness, look, the temperature of the water changed a lot, and the temperature of this thing I put in here didn't change very much. So what does that tell you about the specific heat of the mystery object? Well, you should be saying to yourself, oh, well, this must have a much higher specific heat than the water because its temperature only changed a little bit compared to the water, and you have more than twice as much water uh, as you do of the mystery thing. So it's like the water has 2 counts against it. So that should tell me that the specific heat of whatever I find is going to be much greater than the specific heat of the water. So let's see if in calculations it actually turns out that way. So using, again, our equation M1C1 times T final minus T initial equals negative M2C2 times T final minus T initial, which is our hot thing. This one is going to lose heat, so it goes in on the negative side. So on the cold side, I'm going to have the 200 times 4.18 times, okay, I know the T final this time, right? This is going to be 85 minus 10. And over here, this is going to be negative 75 times C2, the thing I'm looking for, 85 minus 100. Okay, so starting on this other side, right, you're going to have negative 75 times C2 times, what's this going to be, negative 15? So essentially, I'm going to divide this by, so the negatives, I'm going to divide this by 75 times 15, right? Those negatives, you get a double negative there, so those both become positive. So you're going to take this quantity, calculate it, divide it by this thing, and you're going to find that C2 is 55.73 joules per gram degree Celsius. Or in other words, whatever this mystery substance is, it takes 55.7 joules of energy to take 1 gram of it and increase its temperature by 1 degree Celsius. Uh, Water has one of the it basically has it's not the highest, but it is one of the highest specific heats of any uh, quantity. And so for something to have a specific heat that's that much larger than water's and it being solid, which poses another problem that is a little bit beyond the scope of this course. This is an unrealistic specific heat. Um, in the real world, but for the imaginary numbers that I made up, it's fine. And especially we expected this to be really big because of those things we talked about in the beginning, that that the temperature of the water changed so much, and there was more than twice as much of the water as there was of the thing. Anyways, just so that you all know, this number realistically in the real world would be not possible. It's an unrealistic figure, but for the little made-up numbers I have here, it works just fine. Anyways, I hope this was helpful. Again, if you have any more questions about this or how this stuff works, please let either Lou or I know, and have a marvelous weekend.